We will traditionally start with mechanics. With mechanics and mechanics traditionally starts with kinematics. Kinematics is a part of mechanics that studies motion. I will. I think I will. I think I will. I will print. I think I will print about this kinematics. Kinematics is a part of mechanics that motion without taking care about its reasons. Without taking care about its reasons. So what can what else can I say about kinematics? Kinematics is similar to geometry. But the main difference is that the objects in kinematics may move in space and in relation to each other. This is the main difference between kinematics and geometry. And the main object of kinematics is a material point. What is material point? Material point is similar to geometric point, but material point has mass and can move. So material point is a point that has mass and can move and material point is the main model, the main object in kinematics. There are some other objects, for example, perfectly rigid body, or solid or deformable media, or perfect liquid. But these systems may be studied or maybe considered as systems of material points. So material point is a main object and key object in kinematics. And as we learn in motion of material point, we have to define its position in space in some way. We have to define its position. For this, we have to set a reference system, and the simplest way to define reference system is to define is to define Cartesian coordinates. In a three-dimensional space, it can be drawn in approximately in this way. Three coordinate axis. Wrapper point O with wrapper point O. Axes are X, Y, Z, X, Y, Z, and we can define the position of material point with its coordinates. X is equal to X as a function of time. Y is a function of time. And Z is also a function of time. Z is also a function of time. So in this way, we can define the position of material point. There is another way to define the position of material point in space. Another way is to do this with radius vector. What is radius vector? Radius vector is a vector that can be written as x I plus y yod and plus z key. I hope you remember your geometry course, and you may remember that I yod key are orts. Orts they have next properties. The modulus of I is equal to modulus or absolute value of yod, and it's equal to modulus of key, and this is equal to 1 unit. So EJK are unit vectors or orts. And another property of them is that I has the same direction as axis x. Yod has the same direction as axis y, and key has the same direction as OZ. And so we define in this way, in these two ways. We define the position of material point in a three-dimensional space. For example, we can show this on our picture. So material point M has radius vector r. And and these are kinematic equations of motions. Kinematic equations of motion. Kinematic equations of motion. They can be shown in this way. Okay, do you have any questions? Do you have any question? No questions. Okay, and it is also necessary to say that we can I will make I will improve volume. Okay, and it is also necessary to say that we can obtain from this we can obtain trajectory equation. Trajectory equation. Trajectory equation. I will type this. Trajectory equation. Equations may be obtained from kinematic equations of motions of motion by excluding excluding of time. So we can exclude time. We can exclude time from these equations. Exclude time, and we will obtain trajectory equations. Okay, let's say a few words about motion. How to understand this, and how to define, describe this. I will to make it more simple. I will draw two-dimensional system. But for any other system, it can be done in the same way. It can be done in the same way. So let's do this. So I'll define two-dimensional Cartesian coordinate system x, y, and let's imagine that at initial moment in time, the position of material point is this at initial moment on time, and at another moment of time, we have this. We have this position. We have this position. So at initial moment, we have radius vector. We have radius vector R1, and at the final moment, we have R2. And the trajectory of motion, is maybe drawn in some way like this. This is for example, and the length of path length can be signed as some delta s. This is a path length of this way. ds is a path length, and we can also define displacement vector. What is this? Displacement vector is a vector that begins in initial point and ends in final point. So it can be shown in this way. Displacement vector is delta r. Delta r is displacement vector. And as you can see, it is always certain that absolute value of displacement vector is smaller or equal than path length. But we can consider limit. In this way. We can consider such a limit. Delta t is going to, or tends to 0. Delta t tends to 0. Absolute value of delta r. And this is equal to limit delta t tends to 0 delta s. Or we can also write this in short form, like this. dr and this is equal to ds. The similar relation was proved in your calculus course. Calculus sometimes in Ukraine it is known as mathematical analysis. But in European Union or United States, it is known as calculus. So according to mathematical analysis, we have such equation. Maybe you have some questions. No questions. Okay. The motion motion can be also described with average velocity or average speed. Average velocity, what is this? Average velocity. Average velocity. Average velocity is v. Average velocity is equal to delta displacement vector. Displacement vector divide by the time of this displacement, and this can also be written as r2 minus r1 divided by delta t, and this can also be written as r at a time moment t plus delta t vector, and minus r as a function of t divided by delta t. This is average velocity. Average velocity, and here you can see letter v. Letter v is the first letter in a word velocity. Okay, do you have any questions? No questions. Okay, so what can we say about average velocity? Sometimes it is useful, but sometimes not. What is the problem? The problem is velocity may be different. Velocity may be different in different time moments. Velocity may be different, and velocity may be different in different parts of the way that material point passes. So how to solve this problem? This problem may be solved. By taking limit of average velocity, and this limit is known as instantaneous velocity or instantaneous speed. Instantaneous velocity. Instantaneous speed. Instantaneous speed. So we have limit. We have limit v. V is equal to limit of average velocity, and it can also be written as a limit of this relation, of this fraction, and it can be considered as simple simple first derivative. First derivative of velocity. First derivative of displacement vector. This derivative can be written as dr by dt. This is first derivative. Okay, do you have any questions? Do you have any questions about instantaneous speed? No questions. No questions. Okay. Okay, if there are no questions, I think I will clean. I will free some space. I will free some space on my screen, but it is necessary to leave some formula that we will need. So it is necessary to clean this carefully. Okay, I think this will be okay. I think this will be okay. So let's continue. Let's continue this. So let's find the absolute value. Absolute value of instantaneous speed. Before doing this, we can also write this in another way. We can also write this as Vxi plus Vy plus Vz t. And what does this mean? It means that according to previous formula, we can make substitution. We can use this here. And from this we have that we'll write this in a short way. That Vx is the first derivative of x by time. Vy is also the first derivative time, and Vz is the first derivative of z by time. So here we have Vx, Vy, Vz, and they are derivatives of coordinates. of coordinates of material point. Okay, so let's find the modulus or absolute value of vector of velocity. How to do this? V is the absolute value. Absolute value sometimes, no, not sometimes, in many cases, absolute value is much more useful than its vector. So we need some useful formula to calculate absolute value of vector of velocity. Absolute value according to Pythagoras theorem. According to Pythagoras theorem, it may be calculated from coordinates of vector. So it according to Pythagoras theorem, it can be calculated as square root of the sum of squares. It can be calculated in this way. Oh, let's make substitution. Let's use this here, and from here we will have square root of dx squared, or dx to the power of 2 plus dy to the power of 2 plus dz to the power of 2 under the square root and divided by differential of time. And what does this square root mean? It means the modulus of displacement vector. According to this. So we have modulus of dr, displacement vector, modulus of displacement vector, and as you can remember from here, this modulus is equal to increase of path or path length. So it can be written as ds by dt. First derivative of path length. Okay, do you have any questions about this? No questions. Okay. In this case, I can clean some space, or I can free some place on my screen. So we have different formula for instantaneous velocity. Instantaneous velocity may be considered as velocity at the moment in time. I have light was turned off. Okay, do you hear me? Sorry, I have disconnect because the light was switched off. We have trouble with this in Ukraine. So I will disable my video. I will disable my video in order to improve internet connection because it may be unstable, and we will continue. We will continue our lesson. We will continue our lesson. And as I can see, everything has disappeared from my screen. Everything has disappeared, and this is of course this is bad. This is bad, but I will refresh this. Instantaneous velocity. Instantaneous velocity. Instantaneous speed. This is a limit. Limit when time tends to zero. Limit of average velocity, and this is limit time tends to zero. R radius vector at a moment in time of t plus delta t. Delta t is time increase, and minus r at the moment in time t divided by delta t divided by delta t, and this is the same as first derivative of radius vector. The first derivative, and what else? We can also write that v is equal to vx I plus vy dot, and plus v z key. Vz key. Okay, where vx vx is equal to dx by dt derivative. V I will just copy this. I will just copy this 2 times. Maybe it is better to write this here. Write this here. To write this here, and to improve so it will be faster. it will be faster to write this in this way. Y and z dz by dt. And the last thing is absolute value of velocity v is equal to absolute value of vector of velocity or instantaneous velocity, and this is the same as square root of vx to the power of 2 vy to the power of 2 and plus vz to the power of 2. And this is the same as ds dt, instantaneous velocity. And what is necessary to say? It is necessary to say that the direction of instantaneous velocity vector, this direction is the same as direction of displacement vector. It can be written as so the direction of vector v is the same as the direction of displacement vector. These directions are the same. Okay. What to do? If the velocity changes in time? We can also we can describe this change with derivative of velocity, and we can define acceleration or full acceleration. So acceleration is the change of velocity with time, or change of velocity with time. So it can be calculated as the first derivative of velocity. So acceleration a is equal to first derivative of velocity by time. And as you remember from your calculus course, the first derivative of first derivative means the second derivative. So we can use this here. And from here we can get that I'm sorry if you don't have any questions to ask. Could you please disable your microphones? Okay, thank you. So we will continue. full screen. Okay, so we will continue. This is acceleration. This is acceleration, but sometimes, sometimes this formula is not useful. Sometimes this formula is not useful. Sometimes it is useful to look at change of velocity by its absolute value and the change of velocity by its direction. So sometimes it is necessary to separately define change of the direction, change in direction of velocity, and or change of the absolute value of velocity. How can we do this? We can do this in the next way. We can write the acceleration. We can write the acceleration as a sum of two vectors. An, where an is a normal or radial acceleration, and plus a tau, that means tangential acceleration. How to do this? How to do this? How to do this? We can do this. We can do this in the next way. An is v to the power of 2 divided by r multiplied by n. I will show the picture to understand, to help you understand what is n vector, and this is first derivative of absolute value of velocity by time, and it is multiplied by tau. It is multiplied by tau. So where an is equal to this, is equal to this, is equal to this, and this is normal or radial acceleration, normal or radial acceleration, and a tau is equal to dv by dt multiplied by vector tau. Vector tau is tangential acceleration. Tangential acceleration. Tangential acceleration. And what is r? R is is curvature radius. Is curvature radius. And what is n or tau? I will draw a picture. If we have some trajectory, of motion, we have vector of velocity v, vector of velocity. We also have vector of tangential acceleration, and normal acceleration is always has this direction. Normal acceleration of material point has always this direction. And what are n and tau? N and tau are known as tangential and normal unit vectors, and they are equal. They are directed as it's shown here. So this tau, this is vector tau, and this is vector n. And we can also write this that absolute value of tau is equal to absolute value of n, and this is equal this is equal to 1. Okay, and as it is written here, the acceleration is the vector sum of normal and tangential acceleration. So according to this picture, we can conclude that let's we can conclude that acceleration is here. This is acceleration or full acceleration, and according to this picture, we have that this is the right angle, and here we have according to this we can use Pythagoras theorem to make a conclusion that acceleration is equal to the square root of an to the power of 2 plus a tau to the power of 2. A tau to the power of 2. Okay, maybe you have some questions about acceleration. It is a important and but quite difficult things, but I hope we will manage to cope with them. So at least we will try. We will try to understand. We will try to understand this, and I hope this will be this will be useful for you in some way. Okay, so do you have any questions about this? About acceleration and about instantaneous speed? No questions. Okay, if there is no question, if there are no questions, so so let's continue. Let's continue. What else we have to we have to we have to learn today is is rotational motion of perfectly rigid body. What is a perfectly rigid body? A perfectly rigid body is a system of material points that cannot change change their places in relation to each other. I think it is better to type this. Perfectly rigid body. Perfectly rigid body. Body is a system. Is a system of material points. Material points that cannot change their positions in relation to each other. This is perfectly rigid body. So perfectly rigid body, or in simple or simply rigid body, is a model. This is abstraction. And it is not a real object, but many real objects can be described as rigid bodies. Sometimes it is for wheels, or planes, spaceships, so different vehicles can be considered as perfectly rigid bodies. So let's have a look at rotational motion of perfectly rigid body. I will draw a picture. In three-dimensional space. I will draw this picture. Coordinate axis in Cartesian coordinates, x, y, z, x, y, z. Here we have some rigid body, of any form, any form, any shape, and let's define a position. Let's define a position of some point, of some material point of this rigid body. The position of this point may be defined, as you know, with radius vector. With radius vector. And let's consider that the initial position is R1, initial position, and the final position is R2. Is R2. Okay, R2. The final position, and we can also define the position with radius of rotational motion. As you can, I hope you understand that the trajectory of material point, of each material point of rotational body is a circle. Trajectory of each material point of perfectly rigid body is a circle. And so every circle has its radius. So here we can define this radius. This is radius. And radius in final position can be defined as this vector, and radius in initial position is R1. I will show this here. And the path length is some ds. So how to define this ds? It can be defined with radius and angle of rotation. So radius of rotation of some point of rigid body is absolute value of R1, and it is also equal to absolute value of R2. And ds, path lengths can be defined as R multiplied by the d phi. So let's show this picture in two-dimensional view, in a plane view. It can be done in this way. So here we have z, Z. Here we have omega. I will tell what does it mean. Okay, let's consider that the direction of rotation is here. The direction of rotation, and here we have R1, R1, and here we have R1, R1, and let's sign this angle as alpha. So from this triangle, we can see that if we notice that R is equal to absolute value of R1, and it is equal to absolute value of R2. So from this triangle we can conclude that this is equal to d phi r sinus alpha. D phi r sinus alpha. Okay, do you have any questions? Do you have any questions? No. Так. I will. No questions. Okay, thank you. No questions. Okay, that's great. That's great. So we will continue. As you can remember from this red frame, it is written here that the absolute value of velocity is equal to first derivative of path length. So let's use this here. Let's use this here. V is equal to this derivative, and this is equal to d phi by dt r, and this is equal to d phi by dt, r sinus alpha, r sinus alpha. R sinus alpha. Okay, so if we so let's define such value as angular velocity. What is angular velocity? Angular velocity the absolute value of angular velocity, the absolute value of angular velocity, the absolute value of angular velocity. This is is equal to this modulus, and this is equal to this derivative. This derivative. Okay, and what can we say? What can we say about the direction? About the direction of this angular velocity vector. If we have this direction, if we have the rotation the same as right screw, In this case, we have this direction, or we have another direction if the rotation is this. I hope it is clear. The direction of the vector of angular velocity, and we can use this here. We can use this here. To say that v is equal to omega r sinus alpha, and this is equal to omega r. Okay, and how to define the direction of velocity on this picture. We have the direction of rotation that is shown here. This is the direction of rotation. So according to this, we can show the vector v. This is perpendicular to the screen, and it is directed from us to the screen. Vector v in this case is directed from us to the screen, and in this case this is perpendicular to the screen, and it means that according to analytical geometry, this formula may be rewritten in vector form. According to this, we have vector product or cross product omega r, and this is the same as omega cross product r. Omega cross product r. It is velocity. Of any point of perfectly rigid body. Okay, do you have any questions about this? No questions. Okay, so I will clean some place. On the screen. I will clean some place on the screen. I will clean some place, and And let's okay, as you can remember, acceleration. We have a few formula to define acceleration, and we can use this here. We can use this here. We can use this here to define the acceleration of any point of perfectly rigid body. Any point, acceleration of any point of a perfectly rigid body. How to do this? How to do this? Normal acceleration, or I will normal acceleration an is equal to v to the power of 2 divided by r. So according to this we have that this is equal to omega to the power of 2 and r. And tangential acceleration a tau is equal to this is equal to we can no, we will use this, and according to this we have that this is equal to beta r multiplied by unit vector tau. And what is beta? Beta is angular acceleration. Angular acceleration. Angular acceleration. Beta is angular acceleration, and it can be defined. Beta is the derivative or absolute value. Beta is derivative of this, and the second derivative of angle of rotation phi. This is angular acceleration. Okay, so according to this, we have such two formula, and acceleration is vector sum of normal and tangential accelerations, and absolute value of this is the square root is the square root and this is this is equal to r multiplied by square root of omega to the power of 4 plus beta to the power of 2. And this is acceleration of a point of a rigid body. Acceleration of a point of a rigid body. Point of a rigid body. Okay, do you have any questions? Okay, I'll just say a few words about the pre-technical usage of this theory. It can be used, for example, to write the correct drivers for computer mouse. To build computer mouse, and to make it work, properly, we have to define the connection. We have to define the connection, the relation between its motion on the table and between the motion of a cursor on the screen. So for this relation, for this connection, we need to use kinematics that was learned in this lesson. Okay, so do you have any questions? No questions. Okay, if you don't have any questions, so thank you for your attention for today, and I hope to see you next week.
Nice meeting you.
Okay, bye.